Hi everybody. We are going to be talking about section 4.3 today, which is linearly independent sets and bases. And first thing we want to start off doing is talking about linearly independent sets. So let's just remember, right, a set of vectors is linearly independent if and only if whenever you take a linear combination of them. So I take a linear combination of them. The only way to get the zero vector, let's see, so only if all of the scalars are zero, right? So that's a weird way to write it out, but basically the only way to get zero from this is that you have to scale all of them by zero, or if you stick them in a matrix and row reduce, there's a pivot in every column, no free variables. Okay, so let's look at a theorem. A set of vectors in a vector space, v1 through vp, is linearly dependent if and only if the following is true. Okay, so it's going to be linearly dependent if and only if some v sub j, where j is not the first one, it's at least the second one in the list. So some vector somewhere in the list is a linear combination of the previous vectors excuse me, in the list. So notice really what we're saying, right, is that they're dependent if and only if at least one vector is a linear combination of the others. Okay, and we happen to have this nice thing where wherever that vector is in the list, it's a linear combination of the previous ones. You can always get it with just the previous ones and you don't have to use any of the ones after. But you have to have at least two in the list. And for there to be previous vectors, you have to start, be at least the second one in the list. Okay. And let's just look at an example here. So here we have V1, V2, and V3. Okay. And we can first ask the question, is this set with all three of these vectors linearly independent or dependent? And this is one that hopefully you can answer with me. So I'm going to pretend that all of you said linearly dependent. Okay, and why? Well, because any set with the zero vector is in this set. Let's call this set S. Zero vector is in S. Every set with the zero vector in it is linearly dependent. Okay. Two, let's find a VI that is a linear combination of the previous vectors in the list. Okay, so we're finding one that does fit that theorem. And let's see, we've got V3, right? V3 is 0, 0, 0, and we're saying let's get it as a linear combination of the previous one in the list. And the question is, what can go here and what can go here to make this a true statement? Well, I can just say 0 and 0. And now, right, so V3 is a linear combination of V1 and V2. All right. But now what we want to do, right, is I just want to illustrate that this result is at least one. It's not every single vector, okay? So let's look at 3, make sure our vectors are in view. Let's find a VI that is not a linear combination of the previous vectors in the list. And we can't just automatically assume that this is true. And our VI here is going to be 8, 0, and 1. Okay, and we've talked about this some before, right? So we're trying to fill in this, but we're not going to be able to do it because we can sort of look at it component by component, right? If we look at this first one, well, that scalar would have to be a 4, and that would work. 4 times 2 gives us the 8. 4 times 4 gives us 16. So the 4 is actually not going to work. If we look at the second component, it would have to be 0, but then 0 doesn't work for the other ones. If we look at the third component, it would have to be 1/4 to get that 4 to be 1, but doesn't actually work. Okay, and in fact, we can't even make it work at all, right? Let's see, which one is it? V2 is not even a linear combination of the other two, V1, V3. Okay, so this is just a reminder. Linearly dependent doesn't mean everything is a linear combination of everything else. It just means something, one thing, maybe more, but maybe just one, is a linear combination of the other ones. All right, let's now talk about a basis. Okay, basis for a subspace H in V. There's two main things we need for a basis. One is it's a set of vectors in H that are linearly independent. So basis has to be linearly independent. And two, we'll say this set of vectors spans H. So two main things when you're talking about basis: linearly independent and spans H. Okay, right, so this is a main thing. This is a main thing. Basis has two properties. So basically, it's independent, meaning there's no redundancies there, right? Every vector in that set sort of gives you new information. And two, from those vectors, you can get everything in your subspace H. Okay, so it's basically sort of, it gives you not necessarily a simpler way, but it gives you kind of a uniform way to write every vector in your subspace. Every vector in your subspace can all be written as a linear combination of this set of vectors. Okay, and there's a couple of ways that we can sort of think about a basis. Basically, a basis is, one way to think about it is a maximal or a largest possible linearly independent set. Okay, is one way to think about it. Another way to think about it is a minimal or a smallest possible spanning set. Okay. And let's look at the spanning set theorem. So this is still in our same section about linearly independent sets and bases. Okay, so we have a set of vectors V1 through Vp in some vector space V, and we're going to look at the span of that set. And so let's remember, right, span is all linear combinations of V1, V2, through Vp. So that's everything that looks like this, right? It's every possible way you could scale and then add those vectors together. And those are little blanks that we're filling in, right? Not minus signs. Okay. So spanning set theorem is really nice. All right. So there's two things happening here. First, if one of the vectors in S is a linear combination of the others. So sort of the situation we were talking about above, right? If one of these vectors is redundant, then we can basically throw it out and that set still spans H. Okay, then S minus, let's call this vector V sub k. V sub k still spans H. Okay, so what we're doing here is you can throw out redundant vectors without changing the span. All right, great. Now let's look at the second thing. Okay, and the second thing basically says, as long as you're actually talking about an interesting set and not just a zero, right? As long as there's actually stuff in this span, you can keep on throwing out vectors and you'll end up at a basis eventually. Okay. So if your subspace, if your span is not trivial, then there's a basis in there somewhere. Then some subset of S is a basis for H. Okay, so basically you can keep chucking out redundant vectors, we'll say. And you will, for sure, eventually end up at a basis. Okay, so you just throw out redundant vectors until there's a linearly independent set. And let's take a look at an example here, because this is sort of a technical theorem. There's kind of a lot of notation. Okay, so let's look here. We want to find a basis for the subspace of R spanned by these three vectors, and let's call that space H. So H is going to be our span of V1, V2, V3, V4. Okay, so you have two options here. All right. So option one is figure out your redundant vectors by inspection. Okay, so that's just kind of, look at your vectors, see if you see any relationships, and then go from there. Okay, and here, let's see. So this part, right, this -1, 4 looks a lot like this -1, 4. So maybe there's some kind of relationship there between those two. And then this part is sort of like this part up here, but the top is different. And so if we look around, we can see that you can take this one. That's not what I wanted to do at all. I just wanted to subtract. And if we subtract off the second one, right, so here's V1, here's V2, then what we get is 2 minus 2 is 0, 0 minus -2 is +2, -1 minus 0 is -1, 4 minus 0 is 4. Okay, so basically what we're saying here is that V3 is redundant, so we're going to throw it out. Okay, and then spanning set theorem says that V1, V2, V4 still spans our set H. Okay, so now the question is V1, V2, and V4 independent or dependent? If it's independent, then they span and they're independent, so it's a basis. If they're dependent, then we need to throw out redundant vectors. So let's copy down our vectors here that we're talking about. V1, V2, and V4. Okay. And we're looking just sort of by inspection. Do we see any relationships here? Okay, so there's something that's kind of happening, right? Because we see the 2, -1, and 4. Well, if we look at the 6, -3, and 12, we got from there to there by multiplying by 3. Okay, so let's see if we stick a 3 here. What happens? See if we can fill in this linear combination. So 3 times this first vector would be 6, 0, -3, 12. And then the only one that doesn't match up right is the second component, -2. But that's exactly what happens here. Okay, and this would almost work, but when we add those two together, that would end up at 8 and not 6. Okay, so this relationship doesn't quite work. And I'm pretty sure I actually made an error when I wrote this example down. Y'all, it's just like we're in class. Okay, I want to sort of illustrate something. So what we're going to do is we're going to go back and we're going to pretend that all along that was an 8. It's just like we're in class, y'all. Still happens. I'm not going back and re-recording this video. Okay, so now we do the 3 because we still see the thing, the relationship here, and that's 6, 0, -3, 12. And now what we see is that if we just go ahead and add this in, right, we're going to get exactly 6 and 2 is 8, 0 and -2 is -2, -3, or positive 12, right? We get this. Okay, so now V4 is a linear combination of V1 and V2. So we throw out V4, okay, and then we're left with V1 and V2. And the question is now, is this linearly independent or dependent? Okay, and when there's just 2 vectors, you can tell by just seeing if they are multiples of each other. And we can look and see they're not multiples of each other, so they are independent, which tells us that V1, V2 is a basis for our original span H, right? Because when we threw out the redundant vectors, spanning set theorem tells us we don't change the span. And we just threw out vectors, not changing the span. So this is still a spanning set. And then we can verify here that it's linearly independent. All right. What do you do if you can't tell by inspection whether these are linearly independent or dependent? What is the answer to the question most of the time in linear algebra? It's row reduction. So that is going to be option 2. Okay, so option 2 is put V1, V2, V3, V4 in a matrix row reduce it, and the pivot columns are going to form your basis. I'm not going to do that here because you guys know how to do that, but you row reduce, right? You look for the pivots, zeros below here, maybe there's other stuff over here. But in this case, what would happen is, right, 2 of the vectors were dependent, so we would end up with just 2 pivots in our matrix. All right, that is it.